Today's colloquium speaker is Jonathan Lunine, who comes to us from Cornell University, where he is director of the Cornell Center for Astrophysics and Planetary Science. Jonathan's website lists his specialty areas as planetary science. By that we mean planets that you can actually send probes to, theoretical astrophysics, and astrobiology. And I couldn't help but notice that his two books represent two of these fields. One is Earth, Evolution of a Habitable World, and Astrobiology, a Multidisciplinary Approach. Both are available on Amazon, but only the Earth book is on Prime. I don't know why. So I kind of doubt we are going to see a treatise on theoretical astrophysics anytime soon, because Jonathan, well, maybe I'm wrong. No, because Jonathan is so busy with NASA planetary missions and mission studies and serving on high-level review committees, for example, in his role as a member of the National Academy, not to mention teaching. But I should mention, a couple of Jonathan's many honors. The Harold C. Urey Prize in 1988, only 3 years after he submitted his thesis at Caltech. At supper, I want to get the story behind that one. And then more recently, the Cassini Medal Lecture at the EGU last year. So today's presentation will illustrate John's expertise in astrobiology and planetary science, right? Searching for life in the outer solar system. Oh, he's changed the order. Europa, Titan, and Enceladus.
Well, David, thank you very much for that very gracious introduction. And it's a pleasure to be here again. I was here almost exactly a year ago. I gave a talk to the Center for the Origin of Life here at Harvard. And I must say you have done a tremendous job of snow removal. There's not a single patch of snow left. And it only took you a year, so that was, really well done. So I'm going to talk about icy worlds, actually, and I'm going to try to make the case that all three of the objects that are mentioned in the title here, which are actually in the order in which I'm going to talk about them, merit consideration as places to go look for life. And for those of you who have a lot of work to do or a proposal, and you don't want to hear the whole thing, these are the conclusions of the talk. So we have very strong indicators of habitable environments in two outer solar system moons, Europa and Enceladus, and a question mark for Titan, and I'll talk about why it's a question mark there. For Europa, what we don't know yet that is crucial is whether organic molecules, carbon-bearing molecules, are present. We want to confirm the identity of the salts that have been detected indirectly on the surface and in the ocean of Europa, and we want to determine how to access this ocean that, for which there's very strong indication of its existence below the icy crust of that moon. And in fact, happily, we have a mission going there now, Europa flyby mission, that's being readied for launch in the early 2020s. The manner by which this mission ended up in the NASA budget is very messy, but it's there now, and I'll talk a little bit about that. Enceladus, the plume of Enceladus has told us, I think, just about everything we need to know to say that the interior ocean of this little moon of Saturn, with an awkward name, I recognize that, has really everything essential to habitability. Organic salts, heat source, evidence for circulation of water through the rock, and we just now need to go and try to find life, and I'll tell you how, at least in my vision, we want to go do that. And then at the end, I'll talk about Titan. So on this particular slide, which is thanks to UPR, Arecibo, University of Puerto Rico, you have some indication that the amount of liquid water, potentially the amount of liquid water, in the icy moons of the outer solar system is larger than that on the Earth. The little globules or droplets of water that you see are proportional to the volume of liquid water in the Earth, on Europa, or in Europa, and possibly in the interior of Titan. This is a little bit less certain. But in particular, for the Earth and Europa, you see that the amount of liquid water that is present inside Europa is almost certainly twice the volume of liquid water in the Earth's oceans, and because there's only 10% more in the crust of the Earth's crust as well. So this is a lot of water. But paradoxically, the place that is perhaps the most promising target to go look for life, Enceladus, doesn't have very much liquid water simply because it's very small. So the amount of liquid water we think is in Enceladus is about the volume of water in Lake Superior, which is the largest North American Great Lake. Nonetheless, if you're a little microbe, that's a lot of water. So, we certainly can worry a little bit about whether the volume of water matters or not, but actually for Enceladus, it's going to help us, as I'll describe. So let me start with Jupiter's moon Europa, which is about the size of the Earth's moon. It's mostly a rocky world, but it has a thin outer layer, as you'll see in a cross-section, about a couple hundred kilometers thick, of water, ice, and liquid water, and we think now mostly liquid water. It has a very tenuous atmosphere, which is actually not so much of interest to us for the moment, because Jupiter has a magnetic field that is more than 4 orders of magnitude larger than that of the Earth's. That magnetic field is capable of picking up and transporting large amounts of charged particles, which leads to a very lethal radiation environment, lethal not just to humans, but to spacecraft electronics, which is really the reason behind the high cost of Europa exploration. But it seems to have a subsurface water ocean under an ice crust. And so in this particular image, which is from the Galileo Orbiter from the late 1990s, where the color is actually from a lower resolution image superimposed on this higher resolution image about 70 kilometers across, you can see on at least this part of the surface of Europa that there are blocks of material that clearly have been broken apart and rotated. In fact, you can take this image in your favorite image manipulation software, and I guess since we're recording this, I shouldn't advertise individual software, but anyway, open software, whatever you want, cut it into pieces, rotate the blocks, and lo and behold, you can put them back together again so that the fractures actually fit together. And this was done by a graduate student at the University of Arizona many years ago, Randy Tufts. And so this is evidently a region where the crust was at one time mobile enough that these blocks were broken apart and rotated, which is circumstantial evidence for liquid water, but it's not evidence for liquid water today. The real evidence for liquid water in the subsurface of Europa comes from the Galileo magnetometer. In fact, for each one of these 3 objects, a magnetometer or electric field measuring device has played a key role. And I think that's something very striking for those who are interested in space physics, that much of the heavy lifting on this question has been done with magnetometry and electric field studies. So in the case of the Galileo magnetometer, it detected a deflection in the Jovian magnetic field around Europa. This is really an artist's depiction of what might happen to a magnetic field if you have a conductor that's passing through it. And you can look at it as Europa passing through the Jupiter magnetic field, or because Jupiter's rotation rate is actually much greater than that of the orbital rotation rate of Europa, the other way around, the field is passing through Europa. Either way, if in fact there is a conducting layer in Europa, you can generate from this magnetic field eddy currents, an electric field at the surface of the conductor, which in turn will generate an induced magnetic field, as you see in this diagram from a review paper by Cornell et al. And that induced magnetic field, in principle, is detectable as a deviation from the Jovian field, which is mostly a dipolar field. So the actual data that come from the Galileo spacecraft, the orbiter, is quite compelling. These are 2 figures from the Cornell et al. Review chapter, which came originally from the discovery paper in Science. And what you see here are Europa projected on an XY plane. We don't have to worry about the units themselves. This is the size of the Europan disk, obviously. The trajectory of the spacecraft relative to Europa in each case, and the deviation in the magnetic field, the perturbation in the magnetic field from the background Jovian magnetic field. So the solid lines are the measured perturbation with some corrections that are detailed in the paper. And then an induced dipolar field is modeled based on Europa moving through the Jovian field, and that's given by the dashed lines that are a little bit hard to see, but I think you can see that there's a pretty good match. And there are other things going on as Europa passes through the Jovian magnetic field, but what's really compelling about these results are that there's a reasonable match not just for one flyby, but actually for multiple flybys with different angles relative to the orientation of the magnetic field. And in all cases, you get a pretty good job matching this with a perturbation, an induced magnetic field associated with a high electrical conductivity material close to the surface of Europa. And it's not water ice because the conductivity is not high enough, and it's not distilled water because that doesn't work either. It has to be salty water. And it's not a big, thick layer of iron because that would be unstable and would end up falling to the center. So these are the data that suggest pretty strongly that there is a salty liquid water ocean underneath the crust of Europa. So in this figure now, a somewhat artistic rendition of the interior of Europa just points out that there probably is a metallic core, although we don't know that for sure. Most of the interior is silicate, rock, silicon, magnesium, and so forth. And the layer in which you have the ice and the ocean is really thin. We're talking about, again, only a couple hundred kilometers or so. Nonetheless, the size of this body makes this liquid water region, presuming that it's most of this volume outside of the rock, double that of the volume of the Earth's ocean, which makes it a very, very large ocean. Now, why do we think that the crust itself is not very thick? Well, first of all, to get the signature in the magnetometer requires that the ocean actually be substantial in volume and be fairly close to the surface. But also, as you'll see in a moment, there's geologic evidence. Now, do we have direct spectroscopic evidence for salts? In this image here, we see that there's brown discoloration around fractures that may in fact have from time to time admitted liquid water from the interior to the surface of Europa. And then in the substantial radiation environment, obviously there'd be a lot of processing. Unfortunately, the Galileo Orbiter spectrometer, what was called NIMS, was badly affected by the radiation environment, and the spectra were almost all quite noisy. And so there still is a debate about whether spectra in these regions show salts or hydrogen peroxide or organics, although the organics are really a distant third. And so the Galileo mission was a somewhat starstruck mission. The antenna failed to open, as you probably remember. The tape recorder, which was literally a tape recorder, it was the last tape recorder to be flown on a planetary mission, jammed, and in fact was running against the reel for a period of about 12 hours or so. If the tape had broken, that would have been the end of the mission. So getting any of this data back was actually a minor miracle. But nonetheless, we don't know as much about Europa as we really should to assess whether the ocean is habitable. In particular, there is no compelling evidence for organic molecules on the surface, but that's in part because of the difficulties of measuring them with the Galileo spectrometer. Nonetheless, the geologic evidence supports the notion that the crust is quite thin. In particular, in this region, where the short axis is 360 kilometers across, you can see on the surface these cycloidal ridges, which are in a very nice regular pattern. And this is actually best reproduced in a model done by Rick Greenberg and colleagues many years ago by considering the fact that Europa experiences variable tidal stresses. It's in an eccentric orbit around Jupiter, an eccentricity about 1%. And so the tidal stresses that it experiences, of course, changes 1 over r cubed, the force, the tidal force. So there's a substantial difference between the tidal force at the near and far points of Jupiter. And so those variations in a thin crust can lead to fracturing, and in particular can lead potentially to this type of pattern across part of Europa's surface, provided the crust really is thin, namely on the order of hundreds of meters or less. On the other hand, you can find a place on Europa where there's a large impact crater, about the only one. This is called Puil, and it's about 30 kilometers in diameter. It also seems to have a central peak. And I should point out that while the Galileo spectrometer, near-infrared spectrometer, didn't work very well, it clearly showed the signature of water ice, and ground-based spectra clearly show that the surface of Europa is almost entirely water ice. So we really are looking at water ice, and we're therefore looking at topography embedded in and recorded in a water ice crust. For that topography to have remained over a period that is reasonable given this size impact, the crust in this region cannot be 100 meters thick. This is 30 kilometers across. It has to be at least the diameter of that crater, and maybe several times larger. So it's quite evident that there is a large variation in the crustal thickness. Nonetheless, the crust in most places almost certainly is quite a bit thinner than the ocean itself. But the next question is, where do we go to actually sample the ocean? Where are the thinnest places in the European crust? It's probably the cycloidal ridges, but you certainly wouldn't risk any sort of a very expensive lander or drilling system or submarine or something like that based on the knowledge that we have today. And so the next step for Europa, and the step that some of us have been pushing since 1999, the Galileo measurements having been done beginning in 1995, is to send an orbiter to Europa. So we nearly got that. This spacecraft, which has a set of instruments that are symbolized here by acronyms, and the acronyms I will unroll for you in a moment, will not orbit Europa, but it will orbit Jupiter and make many flybys of Europa and be able to do most of the science that some of us had hoped would be done on Europa, with one exception, which is certain kinds of gravity or geodetic measurements are not well performed from a flyby spacecraft. But others are, and in particular, I will point you to the camera system, which is designed to provide a large number of images mapping the entire surface at resolutions of tens of meters. The near-infrared spectrometer, MISE, which I serve as a co-eye on, will finally get us the signatures of organics if they exist and the identity of the salts. In fact, we'll get very good resolution. These are laboratory spectra at the resolution comparable to what we'll get. This is reflectance versus wavelength. The laboratory spectra were collected in two parts, from 1 to 2.5 microns, and then 2.5 out to 5 microns. The instrument spans the whole range. In the 1 to 2.5 micron range, water ice and salts, which you see here labeled in the key, are quite apparent, and the organics are not so important. From about 2.5 to 5 microns, organics begin to dominate, and you can clearly see out to 5 microns the presence of alkanes, benzene, octane, and be able to distinguish those from oxygen-bearing organic molecules. So this instrument is also a mapper, so these spectra will be done essentially as pixels. It's a hypercube where you have an image, and each pixel in the image is a spectrum. And so we'll be able to tell in places where there are fractures whether organics are present and the identity of the salts. There's a magnetometer which will probe more precisely the induced magnetic field. Also, there's a radiation monitoring group of plasma instruments that will provide the flux at the surface. This is important for future lander missions. Ultraviolet spectrometer, and 2 mass spectrometers, one optimized for gas, and remember this name because you'll see it again, mass specs, and one optimized for dust, will be able to sample any plumes if plumes exist. And there was one set of Hubble observations that suggested there might be a plume on Europa. Subsequent observations look like they're arguing against, but if there are any plumes, those instruments will sample them. Even if there are not, sputtering from the surface will provide material that these mass spectrometers can actually analyze. And then 2 instruments for probing the crust, a thermal infrared mapper for looking for thermal anomalies, and a radar that can penetrate down through several kilometers of ice if the ice is clean. So this is very well instrumented. It's really what we wanted to do back 15 years ago. I'm not complaining, I'm just pointing this out. This is actually a mission that was recommended by the Decadal Survey for Planetary Science of the National Academy of Sciences. Despite that, NASA has resisted including it until a congressman from Houston, Texas, John Culberson, who is a huge fan of Europa, he knows a lot about this moon, actually has pushed very hard on this mission and inserted it in the NASA budget and into the law, and therefore it exists. But again, I would emphasize that this was in the Decadal Survey for Planetary Science, and so after 16 years of trying to get this mission going, it looks like it finally will be going. So not much else can be said about the habitability of Europa at this point. Culberson, yes. So we need to know, again, if there are organics. We need to understand and confirm the identity of the salts, which will help tell us whether there are hydrothermal systems, circulations of hot water through the rock, and this all needs to be done with a future mission. So let me move on now to a much smaller moon, not in orbit around Jupiter, but in orbit around Saturn. And this is Saturn's moon Enceladus. It is tiny, 500 kilometers across. Remember that Europa is the size of the Earth's moon, shown here relative to the Earth. This is the size of Enceladus, and you wouldn't think it's a particularly promising target for looking for life. Nonetheless, Voyager images in the early 80s showed that it had some areas that had been wiped clean of craters. It was very bright. It's mostly a water ice surface. It has a density that tells us that it's probably 30% water ice and 70% rock. And it's in an eccentric orbit around Saturn that is quite close to Saturn itself. And so the tidal stresses that it experiences and the potential heating associated with that are quite respectable, on the order of gigawatts of power, essentially. And in fact, it was a magnetometer that first discovered that Enceladus is very active. The magnetometer, and I don't have a figure here, detected a deflection in the Saturnian magnetic field. Remember, we're at Saturn now, which was consistent with neutral particles coming out of a portion of Enceladus and colliding with charged particles and distorting the field. Once that was found by the Cassini orbiter, which was launched in 1997 and arrived at Saturn in 2004, and this discovery was made only 6 months after that. The cameras on Cassini were pointed at Enceladus at high phase angle to maximize the chance of seeing a plume, and here in A and B you see early images from the camera system. This plume of material is at the South Pole. Here the image has been stretched to see the contours. You're seeing here the ice grains that are coming out. The plume is not just ice, it's also gas. The ultraviolet spectrometer on Cassini, by the way, Cassini is essentially 15 years newer technology than Galileo. Galileo was a spacecraft of the 1980s. Cassini is a spacecraft of the 1990s and last decade. Nonetheless, I'll argue it's obsolete in a minute. And then in later images, it was possible to see individual jets where material is pouring out of the South Pole, combining to make this plume. And by the way, I forgot to mention, Enceladus orbits within the so-called E-ring of Saturn. And when that E-ring was discovered, even before Voyager, it was thought that maybe Enceladus might in fact be the source of this E-ring. And now, in fact, we see that this is the E-ring material. Indeed, there are pictures that Cassini has taken from above the ring plane showing this plume tailing off in 2 wings and merging with the E-ring, which is really quite fantastic. The source of the plume material of the jets, and there may in fact be upwards of 100 jets here, is this region which is circumscribed by kind of a pentagon, or maybe it's a hexagon, centered on the South Pole. These transverse fractures, called tiger stripes, are where most of the emission is coming from. And then there are some secondary fractures which have been imaged at higher resolution most recently, where there's also material coming out. So to just be graphic about this, Enceladus is spewing its watery guts into the cosmic void, and of course we want to sample that material, right? I mean, it's just too tempting. So Cassini carried with it to the Saturn system 2 mass spectrometers, devices that sample atoms and molecules and determine their mass over charge. And you can, in fact, design them so that the particles that are analyzed are almost all singly charged, and so you just get the mass. And this is the most robust, simplest, most direct way to sample material in situ. It has a long history in the space program, going back to Viking at Mars and Pioneer Venus at Venus. So Cassini carried 2 mass spectrometers to analyze the atmosphere of Saturn and also to measure dust in the Saturn system. But here is this plume, and after quite a bit of deliberation and discussion with the project, it was deemed safe to actually allow Cassini to fly through the plume and sample the material with its mass spectrometers. And Cassini has done that now 7 times over the past 10 years. The most recent one in October of this last year. The closest distance to Enceladus was 49 kilometers in the plume. And the mass spectrometers, even though they didn't have a very high cadence in their data collection, could actually detect variations in the plume materials. So, you know, they were in the region where you actually have discrete jets. And we learned a lot. One of the things we learned is that there are organic molecules in the plume and not just water ice. So this is not a real mass spectrum. This is a cartoon made up in the form of a mass spectrum based on the Cassini data. The gas mass spectrometer is called the ion neutral mass spectrometer on the orbiter. And this is signal versus mass, here in mass units Daltons. Actually now that's a unit that's discouraged. It's now the atomic mass unit, or U, which are almost the same but not quite. And you see colored here different peaks, actually peaks and valleys that correspond to different classes of material. Cassini is flying through this plume at between 7 and 17 kilometers per second. And so many of the molecules are being fragmented. And so a lot of the analysis and identification of species is based on their fragments, as well as in some cases on the whole molecule itself. So water is shown in blue, fragments of CO2 shown in red, methane and ammonia, those are ambiguous, so we don't have an absolute value for each one, shown in green, a variety of light organics out here, and possibly benzene C6H6. However, this is a mass spectrometer that was designed in the late 1980s, early 1990s. Launch was in 97. It has low mass resolution. It's essentially unit mass resolution, so you know whether a molecule has mass 28, but you don't know if it's 28.002. And for that reason, there are a whole bunch of ambiguities. And so this is a list put together by Hunter Waite, the principal investigator, showing potentially ambiguous species from the ion neutral mass spectrometer. And in particular, CO, N2, and ethylene, C2H4, all have the same molecular mass, unit mass. So we'd like to remove these ambiguities, and I'll get back to that in a minute. But what's important from the INMS data is that there are organic molecules coming out of Enceladus. The Cassini second mass spectrometer, the cosmic dust analyzer, designed to measure dust in the Saturn system, has a collision plate in front of the inlet, and ice particles and dust particles that come in at kilometers per second are broken apart so that the molecules deep inside the grains can be analyzed. And this works great for Enceladus. And one of the things that was discovered is that the biggest ice grains have substantial concentrations of salts. Sodium, potassium, and also chlorine have been discovered. And the percentages are anywhere from 0.5% to 2%. Ocean water on the Earth today is 4%, so this is within an order of magnitude of ocean water. And the smaller grains don't have that much salt. But the larger grains, and here large means a few microns in size, to have that much salt in them must be frozen seawater, because only seawater can solubilize salt to that extent and carry that high a concentration. And so from the CDA results, we think that the largest ice grains indeed are frozen seawater coming from the interior of Enceladus. Now this was quite a discovery at the time, because when the plume was first discovered, there was a big debate about whether it was coming from an interior ocean or simply some sort of pressurized ice in a cold icy crust. And one model that was offered was that it might be clathrate hydrate that was dissociating and driving material out. This discovery is inconsistent with that, and subsequently to all of these flybys, except for the last few, Cassini also made a different set of flybys of Enceladus that allowed the mass distribution inside the moon to be measured. This is done with the Cassini radio science system, which is actually not just a receiver and a transmitter, but the transmitter tunes its frequency to a hydrogen maser system in the Deep Space Network that NASA operates, which allows the frequency to be calibrated to a precision of a part in 10 to the 14, actually better than a part in 10 to the 14. And so it's possible to measure variations in the velocity of Cassini as it's moving through the Saturn system at kilometers per second to millimeters per second, which means that very subtle variations in the mass distribution away from spherical can be determined in icy bodies. And in the case of Enceladus, those flybys, the so-called gravity flybys, plus the measurement of the topography, the shape of Enceladus from the camera, led to the conclusion published by Yes et al. In 2014 that underneath the ice is a higher density and therefore liquid water region concentrated at the South Pole. And a subsequent analysis by Bill McKinnon showed that indeed you could also fit this with a thicker ocean at the pole and a global ocean around the entire body. So this is icy crust, liquid water, and then a rocky core beneath it. The rocky core is needed to fit the density. Now, subsequent to that, work by Peter Thomas and colleagues, mostly at Cornell, again using the camera on Cassini, with a decade of observations, were able to map the libration of Enceladus. The orbit is eccentric, and Enceladus nods back and forth. The amplitude with which it librates is so large that one has to conclude that this icy crust is in fact what's librating, that it is free of the rocky core beneath. Because if the whole mass of the body was librating, it would have to have a much smaller amplitude. It's too massive to have the amplitude that was actually measured from the Cassini images. And so the conclusion is the ocean is global. It separates the icy crust from the silicate core, and the crust slides back and forth. So Enceladus has a global ocean, and that, I think, is the smoking gun that the material that's being sampled by Cassini is indeed coming from that ocean. Much more recently, in a paper by Xu et al., this is the CDA team again, they announced the detection in the Saturn system, and they could kind of piece this back to Enceladus, of very tiny silica grains, SiO2 grains, which have a very narrow size distribution, so narrow that the only plausible way to explain them is that they're a sort of a colloidal suspension in the ocean of Enceladus. And the way that they think these formed is that now Enceladus is turned on its side. This is the rocky interior, the ocean, and the cracks leading to space, is that if you have hot water cycling through the rock, that hot water will leach out silica, SiO2, which will dissolve at those temperatures, 50 degrees Celsius, not Kelvin, but Celsius. And that silica-rich water will then come out, and as it cools, the solubility goes down and the material precipitates out. And it's suspended, and if in fact it were to just sit there, it would grow, and you'd have a broad size distribution, but evidently this material gets shot out through the plume quickly enough that it never grows. And so this is an indication of a hydrothermal system, and that this material is driven out of the ocean fairly quickly. So in summary, what Cassini has found for us is an ocean of liquid water that is global, that has salt in it, that has material coming out into space, that contains organics, that's driven by tidal energy, tidal heating, and for which there are hints of a hydrothermal system at the base. And these samples are free. I mean, you have to pay for the spacecraft, but you don't have to drill. The problem is that these mass spectrometers are old, and they have very low resolution and low sensitivity and narrow mass ranges. So a year or so ago, a group of us proposed to the NASA Discovery Program to go back to Saturn, orbit Saturn like Cassini does, fly by Enceladus like Cassini does, fly through the plume, but do it with mass spectrometers of today. Mass spectrometers that have 2 orders of magnitude higher mass resolution, orders of magnitude better sensitivity, and an order of magnitude better mass range. And that's the plan, and yes, this would be a solar-powered spacecraft. Ask me about that at dinner. The 3 objectives are, first of all, good solid planetary science, measure volatiles that will tell us how Enceladus began and how it evolved. But I want to focus on these other 2 objectives. Habitability, determine the details of the habitability of the ocean. We get it now that the ocean is habitable, but we want the details. And then determine if the plume actually contains chemical signatures of biology. I'll get to that in a minute. This is the mass spectrometer that would be flown. Mass specs is a time-of-flight mass spectrometer, different from the quadrupole mass spectrometers that have been flown before. The advantage of this technique is that it gives us this extended mass range, great mass resolution, great dynamic range. It's been selected for the Europa mission, so NASA is confident that this can fly. And to give you an example of what we can do with it, here's an INMS, an old Cassini mass spectrum. You see at mass 28 a peak. Is it CO? Is it N2? Is it C2H4? All of them have mass 28. Mass specs in the lab at a resolution about a factor of 100 times better separates these peaks, and the C2H4 peak is way out here somewhere. So we would remove all the ambiguities in that table that I showed you on the first flyby. A dust mass spectrometer, again, just like Cassini, a gas mass spectrometer, a dust mass spectrometer. Mass specs is for the gas. ANISA, which is designed at the University of Stuttgart, would be for the dust, and it would have the sensitivity to detect amino acids that are embedded in the ice. Here's a laboratory mass spectrum, mass versus intensity. Here's the amino acid arginine. Here are some of its fragments that have been produced by firing a laser at it, essentially, and simulating the high velocity collisions. And all of these are identifiable and can be pieced back together. So what will we do with this? If NASA approves it, they've already passed on it once, but we have another chance in the New Frontiers program coming up this year. Well, one thing we want to do is determine in detail the habitability of the ocean. What is the temperature? What is the amount of chemical energy? What is the oxidation state, which tells you whether organic molecules can be synthesized? And what is the pH? Actually, Cassini, from carbon dioxide and chlorine, was able to give us a very crude measure of the pH, which is somewhere between 8 and 12, but we want to do better. And so in each of these cases, the blue indicates the molecules or the species that mass specs would analyze, and red or brown indicates what the dust mass spectrometer, ANISA, would analyze. I'm not going to go through all these species, but to a geologist, these are good, solid geothermometers that are used in terrestrial systems. Here we're just trying to look to see whether reduced and oxidized species are out of equilibrium. Here we look at redox pairs to get the oxidation state. That's standard chemistry. And these are all indicators of the acidity. And so, there we go. What we would try to do is build a map of habitability. If you imagine the parameters of habitability as occupying a 4-dimensional space, those parameters I showed you earlier, and we'll project this by having only a single temperature, so it's a 3-dimensional graph. you can imagine drawing contours of goodness of habitability. How close is the bottom of the Enceladus Ocean to a terrestrial hydrothermal system? Here's the Lost City hydrothermal system in the Atlantic. It has a temperature of 70 to 80 Celsius, not very different from what the silica nanograins tell us for Enceladus. It has a pH of around 10 or 11. The Enceladus pH range is 9 to 12, 8 to 12 really. Looking pretty promising, but we don't know what the redox state of the Enceladus Ocean is. We don't know the amount of energy available for metabolism, and we'd like to get this range down. And so the purpose of doing all those measurements is to get us a single point in space, habitability space, for Enceladus. And then for evidence of biological processes, we have no fantasy that the mass spectrometer can be used to sample an organism. It's not designed to do that. We don't think there are enough cells in the plume to even have a chance to sample an organism. Could be wrong. But the strategy here is to look for the molecular patterns of life, to identify what are the essential things that make biochemistry different from abiotic chemistry, and go after those things. And so the three primary tests that we're going to look at are to identify the patterns of amino acids and see if they deviate from abiotic. If you analyze a meteorite that has amino acids in it, or you synthesize amino acids in an experiment, you always get a dominance of glycine. These are relative to glycine. And alanine is next, and some of the more complex amino acids decline. This is a very different distribution than in biological systems, as represented by Atacama and Antarctic endoliths. In this figure from Davila and McKay, you don't see all the amino acids that life uses, just 5 of them, but you get the point here. And why is it that the distribution is so different? And the answer simply is that abiotic chemistry produces amino acids in proportion to the free energy of formation. The easier it is to form an amino acid, the more you get from abiotic chemistry. That doesn't really work well for life because the easiest amino acid to form, glycine, is achiral and is really just kind of a filler in the peptide chains. You really need the bigger, more complex chiral amino acids. So life violates this through its catalytic processes, and we will look for that. Second test, repeating subunits and clustering. Fatty acids on the Earth are made of, actually I should say lipids that make biological membranes have fatty acid tails that have a very striking distribution of carbon number. The even numbered carbons dominate. If instead you make the equivalent of fatty acid alkane tails in a simple abiotic reaction, what you get instead is every carbon number, even and odd, in a kind of a Poisson distribution, which is very typical of abiotic chemistry. So this difference is very striking, and it's used actually to identify terrestrial lipids in the sedimentary record because it's a very robust signature that doesn't degrade and is very different from Fischer-Tropsch. And why does it occur? It occurs because the basic building block out of which these lipids are formed is acetate, which has 2 carbon molecules. And so life synthesizes or grabs acetate and uses it like a Lego set to build its membranes. Not all life does that. Archaea don't use acetate. They use isoprene, which has 1, 2, 3, 4, 5 carbons. And so in the biomembranes of Archaea, the carbon numbers divisible by 5 dominate. So this is very different from the abiotic signature. And, you know, if it's alien life and it uses a 3 carbon number molecule or a 7 or a 12, it doesn't matter. It's not going to look like the abiotic carbon distribution. And then finally, we will look for isotopic enrichments. I'm not going to go through this chart. Suffice it to say that we have ways of distinguishing between isotopic enrichments of the light isotope of carbon, which life prefers. Abiotic processes can mimic this, but by making other measurements, such as the ratio of methane to other hydrocarbons and the hydrogen to methane ratio, we can pull out the biological signature. So again, we use both mass specs and ENISA to make these measurements. Now, what if this is life not like the Earth? Well, the key point of all this is that life builds things in patterns. And as Schrodinger pointed out in his book, What is Life? The essential thing about metabolism is that the organism succeeds in freeing itself from all the entropy it can't help producing while alive, which means that even though life generates entropy like crazy, ds by dt is huge, if you just draw a circle around the organism itself, its entropy is very low compared to the environment and the abiotic systems. And that's what we will look for, is the patterns that personify or exemplify, I should say, a low entropy chemical system. So the amino acids are an example, but if we see other patterns, we'll go after those with the mass spectrometer. So just briefly, before I turn to Titan in the last 10 minutes, we would like to do this at Europa as well. If there's a plume at Europa, mass specs, and the equivalent of a NIGA, which is called SUDA, will be capable of doing that. However, the large grains that we really want to go after, the seawater grains on Europa, because of the high gravity of Europa relative to Enceladus, actually fall out very close to the surface and would not be accessible to the Europa flyby mission. So we've proposed a kind of a CubeSat, a somewhat upgraded CubeSat, to carry a small version of mini SUDA, and again, SUDA is just the NIGA instrument for Europa, that would then sample these plumes at low altitudes. So NASA's thinking about it, but we'll see. All right, let me close with Titan. Titan is an object that has been talked about many times. I'm going to assume that you have had the standard junior level course in Titan here at Harvard, and not tell you all about the dense atmosphere, the nitrogen and methane in the atmosphere, the discovery of the hydrocarbon seas that we now know, thanks to the Cassini radar, are methane and nitrogen. In fact, what I want to say is that Titan also has a liquid water ocean, and I'll get to the role of the electric fields in a minute, but there are really two places where we might want to go look for life on Titan. One is in the ocean of Titan, the problem with this being that it's under a thick crust, and I frankly don't know how or whether we can find any evidence for these on Titan's surface. But the other is the alien seas, the methane-ethane seas. And I talked at length about this a year ago, and I'm actually not going to talk about this today. I'm going to talk about the liquid water ocean. The liquid water ocean is going to be a potentially habitable environment if and only if it's in contact with the rock, because that's the theme of all of these oceans. The Earth's ocean, the European ocean, and the Enceladus ocean. We have evidence in every case that they, in some cases we know, that they are cycling minerals and nutrients from the rock. The problem with Titan's ocean is that if you do a standard model of the interior of Titan, here's a cross-section. Titan has a dense atmosphere, nitrogen, methane. It's got a water ice crust. We see the signature of water ice spectroscopically, and the Huygens probe has actually been there. It's landed. I'll talk about the discovery of the water ocean briefly, but underneath that, because Titan is so much larger than Europa, in fact, it's larger in radius by about 50%. Most of that is actually water, and because this water layer is so big, the pressure is larger than 2 kilobars, and we expect to have high-pressure water ice at the base of the ocean. This is very bad for habitability. To have an ocean that is perched between two water ice layers doesn't sound very habitable. So how do we know there's an ocean? Well, in two ways. First of all, and I don't have a slide for this, we have, from the Huygens probe, measurements of the electric field during its descent to the surface of Titan. That electric field is sandwiched between the ionosphere at the top in Titan's atmosphere and something below the surface, because the electric field doesn't go to zero at the surface of Titan. It's non-zero. And the best model for what's going on is that it's terminated at a conductor below the surface that is salt water. But a better indication of an ocean on Titan comes from the gravity data. Because Titan's in an eccentric orbit, it's possible to measure its deformation as it moves from the closest point to Saturn to its farthest point. That deformation is expressed in something called the tidal love number. For the moon, it's 0.05. For a perfectly fluid body, it's 1. For a decoupled ice shell over pure liquid water, it's somewhere between 0.4 and 0.5. And for Titan, it's between 0.45 and 0.75, based on the Cassini data at the 2 sigma level. That's really squishy. So it indicates there's an ocean, but it indicates there's an ocean which is denser than pure liquid water, because that signal has got to appear stronger than the pure liquid water ocean would allow. And so, in fact, this water ocean is probably overdense compared to pure liquid water. At these pressures, liquid water would range from 1 to about 1.2 grams per cc. It's probably more like 1.35 or even 1.4. Now, another fact about Titan that seems to come out from the gravity data is that not only is it squishy, but it's also puffy. And I'm sorry to use these technical terms on you, but there is no other term. The moment of inertia that has been measured for Titan is larger than that of Ganymede, which is its closest twin satellite. Ganymede's around Jupiter. And in fact can be best fitted by either a mixed rock-ice interior, which makes no sense because having a liquid water ocean, the rock and the ice would separate, or having the silicate layer be charged with water, essentially be hydrated silicates, which would allow it to extend out to a larger radius and give us the high moment of inertia. So this was a model that Julie Castillo and I worked on several years ago. This is a more updated model. What this does actually is it restricts the region of the high pressure water ice to a somewhat narrower range of radius than it would otherwise have. This is the radius for the hydrated silicate case. But still, this is a pretty thick layer of high pressure water ice. However, if the ocean is in fact charged with minerals, that tells us 2 things. First, the water's getting to the minerals and it's leaching stuff out somehow. And secondly, it's denser than simple pure water ice. In fact, the density, the upper range of 1.35, actually exceeds the density of the high pressure water ice that would be in the upper part of that high pressure ice layer, essentially up to here. The density of the water ice becomes greater than that of our 1.35 here. This is a plot of radius versus density. This is sort of our upper value for the ocean. Once we get to ice 6, then that material becomes slightly denser. But that's only a region on the order of 50 kilometers. And so it's not very large. And so if we then imagine that at the base of that, there really is a hydrothermal system of some kind, Titan's a large body, which is providing heat to the system. And furthermore, if we take account of the fact that the presence of salts in this ocean will lower the melting point of the ocean, even in the high pressure ices. So this is a phase diagram of water. I'm sorry it's so complicated. But essentially the temperature at the base of the ocean here puts us just about in the ice 6 field. If we now take account of minerals that will depress the freezing point, we actually, I think, are in the liquid water field. So I haven't talked about this before, and we have to do this quantitatively. The conclusion about the high density of the ocean is quantitative. It's in a paper by Giuseppe Mitri and colleagues, including myself. But this part, I think, because we're so close to the melting point of water, almost certainly this high pressure ice is unstable. And in fact, rather than the model that you see in this slide, almost certainly the water ocean extends down to the hydrated silicates. Now, does that mean there's life? Maybe so. Is there any way that we can get to it? I think absolutely not, unless there's been some large-scale volcanic event that's blasted material out onto the surface. It's frustrating. Of these 3 objects, Titan may be the one that has the ocean for which we will never know the answer as to whether there's life inside of it. And I don't have a solution to that. The thickness of the crust, based on the gravity data, based on this electric field model, is probably 60 to 100 kilometers thick. So that's the story for Titan, not as positive as for Enceladus or Titan, or for Enceladus or Europa. But for those two bodies, the chance that we can sample for life, and in particular on Enceladus, that we can go sample for life in the coming decade, is very, very high. And all of the indicators from Cassini tell us that the ocean of this poor little moon with a terrible, not very Hollywood-style name, all the indicators are that this ocean really is habitable. And so Enceladus is the place that I would go now to test whether life had a second separate origin in our own solar system. Thank you.
You make our efforts to understand the structure and chemistry of exoplanets look pretty puny.
Well, we don't have the data on exoplanets. That's the problem. I mean, we can't fly a spacecraft with a transmitter with a stability of 10 to the 14 past an exoplanet. Not yet.
Okay, this is open for questions. Let's start with Roseanne.
I've heard a report recently, and not being in the field, this is just from the popular press, that above the Earth, there had been evidence of some sort of life, and I think maybe not tardigrades, but some other types of things that had been found. I don't know if that's true. Presumably, you do know if it's true. If it is, would this be at all helpful to you? Whatever process inserted be, but from the reports it sounded like it came from an ocean, and of course you don't have a surface ocean in the world that you're thinking of. But does it open new possibilities?
Well, I remember vaguely reading this, but I don't remember the details. But sea spray and other processes will bring microorganisms up into the atmosphere where they may exist for some period of time. Neither Europa nor Enceladus have significant atmospheres. Everything we're talking about is beneath the surface. Titan does have a significant atmosphere with a lot of chemistry, and it's organic chemistry, but it's really cold. And so if any kind of life exists either in the atmosphere of Titan or in these large seas of liquid methane and ethane on the surface, which again Cassini discovered but I didn't have time to talk about, it's going to be very different at the fundamental molecular biochemical level from life on Earth. It will be organic, but none of the biopolymers that life on Earth uses would work in liquid methane ethane. So I think that probably isn't too helpful in our search for life for those reasons. But it's interesting. I mean, life occurs everywhere on Earth where it can reach. Life seems to occur down deep in the rocks and in the atmosphere. It's pretty amazing.
Over here.
So what is the mass loss rate from those zero jets in Enceladus?
I'm sorry, I didn't hear the...
What is the mass loss rate? So how much?
Yeah. So the estimated mass loss rate, if these occur in steady state over the age of the solar system, is somewhere between 10 and 20% of the current inventory of ice and liquid that Enceladus has today. So put another way, Enceladus might have started out with 20% more water ice than it has today. Now, has the rate been constant over time? It's very hard to know. The only indication we have that the plume has any longevity is from the E-ring, which we've known about for about a half century, and the deposits on the surface around the plume, as imaged by the near-infrared mapping spectrometer. The depth of those suggests that it's been going on at least for centuries, but that's a drop in the bucket compared to the age of the solar system. So the mass of the E-ring, I don't know the actual number, but the mass of the E-ring itself, there are removal processes that lead to the E-ring essentially being very, very tenuous. It's very small compared to the amount of material that Enceladus would put out, certainly over the age of the solar system.
Earl?
How serious a source of heat is the libration of the crust around the ocean underneath supposed to be?
Well, the overall tidal, there's tidal heating, and so the tidal heating is undoubtedly going on in the crust, maybe in the ocean itself. I mean, there are papers about internal waves in oceans generating tidal heating. The maximum amount that people have been able to get from tidal models is on the order of 4 or 5 gigawatts of power. which is about what's measured coming out of the South Pole. And there are, factors of 2 in each of these. But the tidal model seems to fit. The problem is, how do you maintain the eccentric orbit of Enceladus? Because as you extract energy from it, it wants to circularize. And the best indication is that it has a resonance, it has a near resonance with Dione. But it's a near resonance, not a strict resonance.
And one other small question.
Yeah.
Do you have a picture of the crust of Europa put together by this student at the University of Arizona?
I would have to find out. So Randy Tufts tragically passed away of cancer many years ago. His advisor is retired now. I know it's in his dissertation, but whether I can find his dissertation or not, if you send me an email.
Nobody sees it.
It's not, it may not have actually been published. I know it's in his thesis because I've seen it. But if you send me an email, I'll try to find it.
Yeah.
Okay, so you mentioned that due to the lack of particle size distribution, I'll put it that way, in the dust, that material has to be liberated pretty quickly, in the case of Enceladus, from the rock.
Yeah.
And move fairly efficiently through the rock and to the jet.
Well, okay, I'll let you
Because
finish your question and make a
because-
minor correction to
Okay.
that. Yeah,
I understand. I'm trying to
right.
get into my relatively small mind on this. But then it basically means you're streaming material fairly directly from the heat source out,
Yeah.
not allowing any dust to build up. So how can you have life build up if basically you have this cycling this so quickly?
Right, okay, so that's a very good question. So, of course, what the picture that's imagined is that the water goes into the rock. It's heated by the rock, and the silica is leached out. And then as the silica, which is dissolved, gets into the ocean and gets to the cooler regions, it begins to precipitate. And then that material is driven out before it has a chance to agglomerate. So in terrestrial hydrothermal systems, some of the terrestrial hydrothermal systems were first detected indirectly by warm pools of water at the surface of our ocean. And so, there are plumes of material that kind of move up pretty quickly, and presumably that's where these silica nanograins are coming from. There are other particles that are larger, that have mostly organics, that were detected by the CDA or ICE. So presumably it's a hodgepodge, but there is, at least some material that's on a conveyor belt, a hot plume of some kind that's getting out fairly quickly. So, does the life end up taking this ride and dying? Hydrothermal systems on the Earth, the Lost City, for example, things literally cling to the mineral structures, and that's how they feed off of them, because if they come loose, they would be moved away from the system. So presumably our putative Enceladus life forms do the same thing.
Okay, just a couple more. Gary, and then over here.
I don't know the details of the radiation environment around Jupiter, but is the presumption that it's well attenuated so that it would not be a lethal environment at the depths of even the shallowest parts of the ocean?
Yes, in fact, even at 100 meters or so, it's attenuated significantly. Now, what's interesting though about that environment is that the radiolysis, of course, produces large amounts of very oxidized species like peroxides. And if those make their way into the crust and down into the ocean, they're a source of energy for life. And in fact, there have been some papers written on this. So radiation for these, again, putative Europan life forms in the ocean, radiation could be a good thing because it could be providing chemical energy.
And one last.
When you discussed the mass specs instrument
Mhm.
on the Europa mission,
Yeah.
you gave the impression that the outlook is somewhat bleak in the absence of a fantastic plume or in the absence of this modification to the mission where you could go to lower altitudes. What is the expectation for that experiment?
Okay, so mass specs was selected without a presumption that there was a plume because they made the case that surface modification processes, radiation sputtering, and even evaporation would provide enough, and there is an exosphere obviously, would provide enough material that it would be able to sample that. The problem, of course, with correlating that with an ocean is that you get this large mixed material up in the exosphere and you don't know where that material came from. So it would be better to have a plume, obviously, but we don't know if Europa is going to deliver that. I think from the point of view of a life search on Europa, the possibility of detecting organic molecules or organic fragments in the mass spectrometer from sputtered material, just carbon and nitrogen bearing compounds. That would be a big discovery.
So Jonathan will be here tomorrow. He has at least one slot still open in the afternoon.
I think it got swallowed up, but come and talk to me anyways.
Right,
Yeah.
and we have one more spot open in the colloquium dinner, so if you'd like to go out for dinner with us, come up and see me. Let's thank Jonathan again for